All right, welcome to This Explainer. Today, we are going to completely dismantle the single most common misconception in DevOps using actual Linux kernel primitives. We're going to build the right mental model from scratch so you can see exactly how things actually operate under the hood.
Okay, so you've probably heard this quote a million times. Containers are just lightweight virtual machines. Honestly, you'll see this framing everywhere. It's in blog posts, job descriptions, conference talks, you name it. But I'm here to tell you right now it's fundamentally wrong. And worse, it sets you up for some pretty critical architectural mistakes when you build your cloud deployments on a flawed mental model.
Think about it like this. A virtual machine requires full hardware emulation, running its own completely isolated guest kernel right on top of a hypervisor. It is literally a computer inside a computer. But a container? A container is completely different. It's just a native process sharing the host kernel under a set of strict rules. A container has never had its own kernel, and there is absolutely zero hardware emulation happening.
So here is our roadmap for today. We're covering 1. The virtual machine myth. 2. Proving isolation with namespaces. 3. Troubleshooting resource limits. And finally, 4. Shared kernel security risks. Let's get into it.
Section 1. The virtual machine myth. Let's talk about the real, physical cost of VM emulation, which is massive. Every single virtual machine requires at least 1 to 2 gigabytes of RAM minimum, just to run the underlying operating system. Think about that for a second. If you have a tiny Node.js microservice that only needs, say, 50 megabytes to actually run, you are still paying a 1 to 2 gigabyte tax per VM just to boot up the guest OS underneath it.
Now, because containers skip that guest OS and hypervisor entirely, they launch in milliseconds using strictly your application's memory footprint. System calls from a container hit the host kernel directly. There's no emulation layer to boot up at all. That means a VM might take up to 2 whole minutes to become ready, while your container is up and running in about 100 milliseconds.
And this incredible efficiency? This is exactly why Kubernetes can so easily pack hundreds, sometimes up to 1,000 microservice containers onto a single host node, where you might only fit 20 VMs. Without the bloated overhead of a guest OS dragging down every instance, your server density absolutely skyrockets, and you literally only pay for the memory your app actually consumes.
Moving right along to Section 2, Proving Isolation with Namespaces.
Okay, so you don't just have to take my word for it. We can actually verify this live on the command line. First, we start up an Nginx container. Then, we use the docker inspect command to essentially ask the host for the container's real process ID. Finally, using a built-in Linux utility called nenter, we can step directly inside the container's isolated view of the world right from our host.
The results here are honestly eye-opening. You'll see the exact same Nginx process running as PID 8821 on your host machine, while inside the container's illusion, it genuinely believes it's PID 1. But it's the exact same process. You can literally run a kill command on PID 8821 from your host machine, and boom, your Nginx container stops. It's not hiding inside some emulated VM layer.
So how does that work? Well, this illusion is created entirely by Linux namespaces, which simply trick the process into seeing its own isolated network, file system, and process tree. The container isn't isolated by hardware boundaries, it's just looking at a filtered view of the host system. It thinks it has its own root directory and IP address, but really, it's just the host kernel handing it a unique pair of blinders.
All right, let's look at Section 3, Troubleshooting Resource Limits.
Now, if namespaces control what a container can see, C-groups control what it can actually use. Control groups, or C-groups, are pure kernel enforcements that prevent a single rogue container from stepping out of line and starving every other service on the host. Think of them as the traffic cops of your host kernel. You can tell the kernel, hey, this specific container is only allowed 128 megabytes of memory or a maximum of half a CPU core.
And this right here is a massive troubleshooting tip. When your process unexpectedly terminates or just slows to a crawl, it is usually C groups at work. If your container hits that hard 128 megabyte memory ceiling, the kernel's out of memory, or OM killer, fires, and it kills the process instantly. No warnings. But on the flip side, if your app is running super sluggishly, you'll want to check its CPU C group quota because the scheduler will just silently throttle it down without ever actually crashing it.
Finally, Section 4, Shared Kernel Security Risks.
We absolutely have to address the high-stakes side of this shared architecture. Unlike a virtual machine where a kernel panic or an exploit is safely trapped inside the guest OS, a container is making system calls directly to the shared host Linux kernel. And that creates a potential single point of failure. Because every container on a host leverages the exact same underlying kernel, a severe vulnerability that allows a container to escape its namespace gives an attacker access to the host and, by extension, literally every other container running on that machine.
So the crucial takeaway for your own architecture boils down to this. You should definitely use VMs to strongly isolate untrusted third-party code, which is exactly what cloud providers do with hardware-level isolation. But you want to leverage containers when you own the microservices, when you need those instant startup times, and when you want to pack your servers for massive, massive scale. For trusted internal environments, containers are for sure the absolute right choice.
As we wrap up this explainer, I want to leave you with a pretty provocative architectural question to help you evaluate your own deployments. Are you running untrusted code on a shared host kernel? Because understanding the difference between hardware emulation and namespace isolation, it isn't just trivia. It completely shifts how you build, debug, and secure production environments. So take a hard look at your architecture today with this new mental model.